A question that has been asked again and again in recent years is why, in systems physics, we do not start with Newton's second law like everybody else. This law states that a force causes acceleration. The corresponding formula is F equals m times a. So, let us discuss the three symbols of the formula F equals m times a individually so as to justify why we do not start with Newton's second law. In our first example, a bird flies into a fighter plane. This raises the question of what happens to the mass. Can this occurrence be described by the formula F equals m times a? Or wouldn't it be better if we used a physical law in which the mass can also change during the process? In a second example, a ball hits the head of a soccer player. Newton's second law says that A equals F divided by m. But which acceleration is actually meant here? The front part of the ball experiences very great acceleration, whereas the rear part is decelerated much more slowly. It can be argued that A stands for the acceleration of the center of mass. In this example, however, the center of mass is not body fixed but moves through the ball during the impact. Therefore, knowledge of the acceleration of the center of mass contributes little to the understanding of this process. The most important objection concerns the force. What is understood by F? Most young people who come to a University of Applied Sciences do not know what a force is. Their explanations are usually confused or simply wrong. This can be demonstrated by taking the example of the inclined plane. This illustration found on the internet is from the German-speaking area. A freshman's illustration could look very similar. Three forces are marked: weight force, friction force, and grade resistance. If these three forces are added together, we see immediately that the resulting force does not point in the direction of the acceleration. The forces are wrongly marked. If even teachers make such terrible mistakes, how are students supposed to understand what a force is? The second illustration, in which all forces are correctly marked, is from an English-speaking area. The body is affected by the weight force and by a force from the support. The second force can be divided into the components of normal force and friction force. To summarize, there are at least three reasons why we do not start the course with the formula F equals m times a. The first reason is F, since this difficult term is often not understood or not understood correctly. The second reason is m, since there are processes in which the mass changes. The third reason is A, since A stands for the acceleration of the center of mass, and this center often passes through the body. These three reasons keep us from starting the lectures on mechanics with F equals m times a. Instead, the concept of momentum is introduced first. In the next half an hour, you will see that the system dynamic approach to physics is much broader than the classical approach, and that systems physics introduces terms and laws with which more phenomena can be understood than with Newton's laws. First, a preliminary remark. On the 16th of May of 1901, Albert Einstein started to work in Switzerland as a supply teacher at the Technikum, the School of Engineering in Winterthur, where he taught mathematics for 2 months. In 1905, Albert Einstein compared mechanics with electrodynamics. He concluded from his results and following Ernst Mach's ideas that all laws of nature, not only the laws of mechanics, have to take the same form in every inertial reference frame. If this idea is thought through, the conclusion can be reached that the velocity of light has to be the same in every inertial reference frame. This constancy of the velocity of light contradicts our experience. This can be illustrated by an example. Let us assume that a bright shining star flies towards us at half the velocity of light. If the velocity of this light is measured on Earth, it moves as fast as the light of a fixed star. This observation contradicts our everyday notion that a cannonball fired from an airplane is faster than a cannonball fired from a stationary cannon. Space and time can be summarized as spacetime, and the condition can be set that the velocity of light in this spacetime does not depend on the coordinate system. The standard time is multiplied by the velocity of light so that the relativistic time has the same unit as the length. Therefore, 1 second equals about 300 million meters. It is difficult for us humans to understand the theory of relativity because in space we can resolve about 1/10 of a millimeter, but in time we can only resolve 1/10 of a second, which equals 30 million meters. A further conclusion from the constancy of the velocity of light is the equivalence of mass and energy. Einstein did not claim that mass can be converted into energy. He stated that the energy content determines the mass of a body and that energy is heavy and inert. In addition, mass and momentum form a four-dimensional vector in spacetime. And this is now the essence of the message. If mass is part of the four-dimensional mass-momentum vector, there is no reason to introduce momentum differently than mass. Consequently, momentum is just as much a fundamental quantity of mechanics as mass is. Therefore, momentum is, just like mass, one of the main physical quantities. A helicopter is hard to fly. It can move in all three directions and rotate around all three axes. According to these 6 degrees of freedom, the helicopter can store 6 basic substance-like quantities. 3 substance-like quantities constitute the 3 components of momentum, and 3 substance-like quantities are part of the angular momentum. Momentum and angular momentum add up to 6 scalar quantities that do not need to be derived, but which can be found and identified in nature. The angular momentum will not be discussed until the second semester. The momentum determines the motion behavior of a body. The mass represents the corresponding capacitance and the velocity the potential. So the x component of the velocity shows us how much x momentum a body of a certain mass is storing at that moment. An analog statement can be made for the y and z directions. With the help of a global coordinate system, the momentum can be divided into its 3 components, which can then be balanced as independent substance-like quantities. An important tool of systems physics is a liquid representation or fluid image. Once we have understood the liquid representation, we can understand many phenomena of mechanics intuitively, and we do not need a lot of formulas. Here you see the liquid representation of a starting car. In the liquid representation, the momentum is represented as a heavy liquid and the car as a cylindrical tank. The mass of the car appears in the liquid representation as a cross-section of the tank, and the velocity turns into the fill level. The acceleration appears in the liquid representation as velocity. The car has to get the momentum from the ground. This happens with the rotary motion of the wheels. The corresponding momentum current is called friction force, since the respective force between the street and the wheel is called static friction force. The momentum is taken from the ground, but the energy has to be provided by the engine. By means of this energy, the momentum of the ground is pumped into the current velocity of the car. The faster the car drives, the more energy per momentum amount is needed. The momentum current strength is measured in newtons. Some of the momentum flows back to the street as so-called rolling friction. Some flows into the surrounding air. The corresponding momentum current is called air drag. Since momentum constantly flows away via air and street, the engine has to constantly pump momentum out of the ground and into the car. If the car goes very fast, much momentum flows into the air. In addition, the momentum to be supplied must be pumped up higher. The momentum content equals base area times height or mass times velocity. A heavy vehicle can therefore store more momentum than a light one with the same velocity. And now the momentum balance can be formulated. The sum of all momentum current strengths equals the change rate of the momentum content. The momentum current strengths relative to a body are called forces. Since the momentum equals mass times velocity, and since the mass remains constant, the change rate of the momentum content can be expressed as mass times acceleration. As a result, the basic law of mechanics can be formulated. The sum of all forces equals mass times acceleration. This law is not meant to be a fundamental axiom. In fact, this formulation is rather the result of a balance equation and the law of capacitance. In the liquid representation, the acceleration appears as velocity. When the acceleration is positive, the liquid level rises. When it is negative, the level falls. Another quantity that we are going to talk about in the next lecture is energy. Depending on the velocity, energy either accrues or flows off together with the momentum. Velocity is the energy charge measured of the momentum current, meaning that the energy flow equals momentum current times velocity. The faster the car moves, the more energy accrues or flows off together with the momentum. Energy flow is measured in watts. The energy flow assigned to the momentum current is also called power of force because the strength of the momentum current relative to a body can be described as force. Kinetic energy is directly visible in the liquid representation. The kinetic energy corresponds to the work that is needed to pump the momentum out of the ground into the car. This work equals momentum times mid-pump height, so mass times velocity times half velocity, or half mass times velocity squared. Kinetic energy can be compared to the potential energy of a tank or to the energy of a capacitor. For the sake of completeness, the energy balance should be mentioned here as well. The sum of the powers of forces is equal to the alteration rate of kinetic energy. We are able to understand overrunning collisions of freight wagons with the aid of a fluid image. Here you can see the liquid representation of such an impact. The colliding wagon with the mass m1 has a momentary velocity of v1. The wagon that was initially at a standstill has the mass m2 and a momentary velocity of v2. At the moment, a momentum current is flowing through the buffers. As a result of the momentum current, the momentum diminishes in the first wagon and accumulates in the second. The circulating momentum current times the momentary velocity difference between the wagons equals the power that is being released in the buffers at the moment. Our second example is taken from Swiss history. After the legendary apple shot, William Tell was bound in chains and led away across Lake Lucerne by Gessler, archenemy of the Swiss nation. When a storm approached and the boat came closer to the bank at Sisikon, Tell was able to save himself with a powerful jump onto a rocky ledge. The fact that William Tell had a brother named Tro, who happened to be standing on this very ledge, was unfortunately to be forgotten. Tro jumped onto the boat at the exact same moment as William began to jump too. Tro was never to be seen again. Because we Swiss love the heroes and condemn the losers, we erase Tro from our history books. Let us examine this historic double jump in the liquid representation. The positive direction points from the boat towards the ledge. When William jumps, a certain quantity of momentum is withdrawn from the boat. Simultaneously, his brother Tro emits about the same quantity to the ledge. William's momentum is then transferred to the ledge. When landing on the boat, Tro withdraws momentum from the boat in order to adapt his velocity to the velocity of the boat. Afterwards, the boat has the same weight as before, but moves faster than it would have done with only William jumping. This example demonstrates the momentum transfer. Although William's momentum is positive and Tro's negative, in the end, both have transferred momentum from the boat onto the rocky ledge. The same happens with gas, where the molecules transfer the momentum only forward and never backward, regardless of their direction of movement. Momentum is not only transferred by the molecules of a gas or a liquid, but can also pass through solids. The drawing shows a freight wagon which collides with another wagon. Both wagons carry a block which is attached to them by a spring. The positive direction points from left to right. When the two wagons collide, momentum is transferred from the left block and wagon to the right wagon and block. Now we will examine the effect of momentum when it is transferred through bodies. The momentum flows from one block backward through the spring and then sideways into the wagon. Then it flows forward through the buffer into the second wagon. Then again sideways, and finally backward into the other block. We can now see that the backward flowing momentum current puts the bodies under tension. The forward flowing momentum current strains the buffer with pressure, and the sideways flowing momentum current generates bending. Bending has also something to do with the angular momentum. Let us briefly turn our attention to the friction surface between block and wagon. There, the sideways flowing momentum current generates shearing. The collision process can also be described in the liquid representation. At the moment depicted in the drawing, momentum is flowing downward. This is the reason why both springs, the buffer and both friction surfaces between block and wagon, absorb energy. Such complex processes may be illustrated by means of the momentum current illustration and the liquid representation. Let us now investigate how the momentum flows through a body. What you can see here is how the x momentum in a metal plate, which is under tensile stress, flows backward, that is, against its own direction of reference. One reflux can be noticed wherever the momentum flows around the hole. This reflux is related to the y momentum current. Figure 2 shows the eddy currents of the y momentum. These eddy currents are induced by the x momentum current, which is flowing sideways. Wherever x momentum flows in the y direction, y momentum must flow in the x direction. This physical law, which is called the law of complementary shear stress, couples the momentum currents of the different components. The figures shown here were calculated with COMSOL's finite element program. If the metal plate is now cut in two on one side, the momentum can only flow around the hole on the other side. As a consequence, the momentum current is pushed to one side even harder, and the eddy currents become more intense. Figure 4 shows the eddy currents of the y component. Let us now return to the overrunning collision. Now we want to explain what forces are. Therefore, we draw a free body diagram for each body. Although all forces are indicated here, only the forces which act horizontally are part of the momentum currents in this figure. A momentum current flows out of the block and via the spring off to the wagon. The strength of the outgoing momentum current is symbolized by a force vector pointing in a negative direction. The momentum current which enters the wagon leads to a positive force vector. The same rule can be applied to the buffers and the other spring. The momentum current which flows out of the left block downward to the wagon is described with two additional forces. The red force describes the outflow, while the green force describes the inflow. These two forces form an interacting pair in terms of the third of Newton's laws. Note that the arrows point horizontally even though the momentum flows downward. The relation between force and momentum current will be explained again using an easier example. Jane and Mehmet are playing tug of war. The positive x direction points to the right. The momentum flows backward since the rope is under tension. This momentum flows out of the ground where Mehmet is standing, and it flows back into the ground where Jane is standing. If they were standing on a skateboard, it could be observed how Jane would move in a positive direction and how Mehmet would move in a negative direction. This is the result of the momentum exchange through the rope. In a game of tug-of-war, the momentum current is closed via the ground. As a consequence, the ground is pressed together. We can now formulate the first rule. Tensile stress means that momentum flows backward. Compressive stress means that momentum flows forward. What is the relation between the momentum current and the forces? A force is a momentum current strength which relates to a system. Where the momentum current enters the ground near Jane, this can be described with a positive force vector. The momentum exit is marked by a negative force vector. The same rule can be applied to the rope. Momentum entry results in a positive force vector. Momentum exit results in a negative force vector. The third of Newton's laws says that momentum has to be of the same strength in opposite directions if it is measured from the two different bodies. Let us now formulate the second rule with reverse causality. Force vector pointing forward means momentum inflow. Force vector pointing backward means momentum outflow. This rule is valid for all three force components, that is, for all three momentum currents. Let us now turn to Newton's laws. The first law postulates that a body which does not exchange momentum with its surroundings maintains its state of motion. The second law can be divided into three parts. The momentum balance forms the first part. According to the momentum balance, the sum of all momentum currents is equal to the change rate of the momentum. The second part describes the law of capacitance, according to which the momentum equals mass multiplied by velocity of the center of mass. The third part concerns kinematics. Velocity equals change of place per time. This three-part statement is easier to understand and much more general than F equals m times a. The third law says that the momentum current strength is the same regardless of which side it is measured from. Now we need some more laws that directly describe momentum currents. The first group of laws we will look at deals with the elastic behavior of bodies. The spring pictured is under tension, which means the momentum flows against its direction of reference. By linking the momentum current with the displacement, we obtain the force displacement diagram. As long as the displacement increases linearly with the force or the momentum current, this correlation can be expressed by a simple law. Force equals spring constant multiplied by displacement. In contrast, the law of elasticity cannot describe the behavior of a rubber band. Also, the behavior of a rubber changes with temperature. As long as a component's elastic behavior can be illustrated by a single line in the force displacement diagram, its reaction is fully elastic, which means that it does not dissipate any energy. Here you can see a shock absorber. When the momentum flows through the shock absorber, the piston moves into the cylinder and oil is ejected through the holes in the side. As the piston enters the cylinder, it covers more and more holes. Consequently, less oil is ejected. In this way, the momentum current stays at a fairly constant level. Let's have a look at the different laws of damping in the force-velocity diagram. A shock absorber filled with viscous liquid shows the simplest behavior. In this case, the force increases linearly with the relative velocity. This means that if the velocity is doubled, the force or the strength of momentum current also doubles. The second curve shows the effect of air drag, which increases quadruplically with velocity. Doubling the velocity leads to a quadruplication of the force. The most difficult friction to model is dry friction, which is described in every textbook. The dry friction force depends only on the direction of the velocity, but not on its magnitude. As the velocity approaches zero, dry friction increases slightly. At standstill, static friction, which can take any value up to a given maximum, becomes effective. Thus, dry friction consists of kinetic friction and static friction. This picture shows the system dynamic model of a two-mass oscillating system. The model focuses on the momentum balance of the two bodies. Tanks and pipelines illustrate this balance. Velocity is calculated by dividing momentum by mass. Since the relationship between velocity and position is the same as the relationship between current and content, we can use the tank pipeline structure to calculate the position. The relative velocity determines the damping behavior of the system, and the distance determines its elastic behavior. This means that relative velocity and distance define the strength of the momentum current between the two bodies. K stands for damping constant and D stands for spring constant. In this model, we apply the simplest laws: linear friction and the linear spring law. Let's have a look at the simulation results. The red line indicates the velocity time behavior of the left body, while the green line indicates the velocity time behavior of the right body. The black line shows how the strength of a momentum current changes over time. The left scale indicates velocity and the right scale indicates the strength of the momentum current. As you can see, the change in velocity of the green body is more pronounced. This is because it has less mass than the red body. Now you should be able to analyze complex processes. The upper diagram shows the velocity time behavior of two freight wagons. The heavier wagon is crashing at full speed into the lighter one, which has its brakes on. The velocity time diagram is essential for motion analysis. On the one hand, it indicates the fill level of the liquid representation. On the other hand, the diagram also indicates the acceleration, which corresponds to the slope, and the distance, which corresponds to the area under the curve. At the points of intersection of the two curves, the buffers are compressed most. The lower diagram shows the behavior of force in relation to time. It is clearly visible that the force is greater when the buffers are compressed than when they are returning to their initial position. This example allows us to ask some questions. How can the displacement and the acceleration of a wagon be calculated? How great is the force that acts on one buffer plate at 0.2 seconds? How great is the momentum that flows through the buffers at the second impact, at 2 seconds? How great is the frictional force that acts on the second wagon at 1 second?